So welcome back everyone, and a special welcome today to our special guests, a fake choir. They're going to be helping us demonstrate some of the concepts. And so let's try to remember what we were doing last time. So we had discussed basically the idea that certain pairs of notes sound nice together and come up all the time in our music. And the most common musical intervals, so that is a pair of notes with different frequencies, the most common and prevalent musical instrument intervals that show up are those where the ratio of frequencies for the two notes is very simple. It's built from very simple whole numbers. So the octave, that corresponds to just a 2-to-1 ratio where the top note has double the frequency of the bottom note. The perfect fifth, that corresponds to a 2-to-3 ratio. The top note has a frequency which is 50% higher. The perfect fourth is a 4-to-3 ratio. The major third is a 5-to-4 ratio. A sixth is a 5-to-3 ratio. And then the minor third is a 6-to-5 ratio. So those are some of the most common intervals, and we're going to talk about a few more intervals later on, and then we're going to get into talking about how these intervals can be combined in order to form collections of notes that we refer to as scales, and also combined and played at the same time in order to make what we call chords. Okay, so maybe just a quick review of why these pairs of notes might sound good to us. We had a couple of different ideas. One was that in the harmonic series, so the series of pure tones that are present when you have a single musical note, you already have these notes, these pure tone frequencies in simple ratios. Since the frequencies for all of the higher harmonics are multiples of that fundamental, if you look at, say, the second and third harmonic in the series, then those two have already a 3-to-2 ratio. So that already defines a fifth, and the third and fourth note define a fourth, and so on. So when we hear these notes with the simple ratios, we're actually used to hearing those combinations of frequencies together, even when we're listening to just a single musical note, as long as it's not a pure tone. And so maybe another reason why these notes with simple frequency ratios sound good together is that if you think about notes, again, that are not pure tones, so say a fifth, and so you think of all of the harmonics that are present in the bottom note and all of the harmonics that are present in the top note, then what you notice is that for these simple ratios like 3/2, then the harmonics either line up perfectly with each other or they fall right in the middle of two other harmonics. And so you don't get any of the harmonics which are close to each other but not equal each other. Because remember, we understood that in that case, you end up with some dissonance or roughness that comes from those two frequencies kind of competing to excite the same region on the basilar membrane. Okay, so when we think about starting with these intervals, and then we're going to be talking about constructing scales out of those musical intervals, a useful concept will be the idea of combining two intervals. So we can do something simple like take an octave and then go up another octave. And a really important idea is that when we do that and we want to figure out what is the final frequency of the top note, what we want to do is start with the first note, and then you want to just multiply the frequency ratio for the first interval by that note, and then multiply the frequency ratio for the second interval, and that gets you your final frequency. So for 2 octaves, you want to take 2 times 2, and that gets you the ratio of your final note frequency to your original note frequency. For 3 octaves, it would be 2 times 2 times 2. And so that would be 3 octaves higher means 8 times the frequency. 4 octaves higher, 16 times the frequency. So this is important. We don't just keep adding a certain amount of hertz. We want to be multiplying. Each time we add on a musical interval, we're going to be multiplying by this certain frequency ratio. And similarly, if we go down an interval, so say going up a fifth and then down a fourth, so that would be multiplying your frequency by 3 halves and then dividing by the fourth ratio, which is 4/3, or equivalently multiplying by 3/4. And so in that example where you go up a fifth and down a fourth, that ends up giving you a frequency which is 9/8 times the original frequency. So just as an exercise, see if you can work this one out. So you start out with a person playing a note with frequency 800 hertz. That's Jeff. And then you have someone else, Tina, who plays a note which is up 2 perfect fifths and then down an octave from Jeff's note. And you want to calculate what is the frequency of Tina's note. So pause the video, see if you can work that out, and then I'm going to talk through it. Okay, so basically what we want to do is start with our frequency of 800 hertz. And then because we want to go up 2 perfect fifths, we want to multiply by 3 halves. And then we're going to multiply by 3 halves again. Okay, so that'll get us to the note which is 2 perfect fifths up from the original note. But then we want to go down an octave, and so we're going to divide by the ratio that corresponds to an octave, which is 2. So we're going to divide by 2, and then finally you work that out and it gives 900 hertz. Okay, so it's good to be able to figure out how to go up and down various numbers, various intervals. Okay, so this example is actually an important one because it's what defines what we refer to as a major second, or more commonly as just a tone in music. So you can actually equivalently say that you go up a fifth and down a fourth. We worked out that that was a 9/8 ratio. Or the one we just calculated, up 2 fifths and down an octave. I spelled octave wrong. So that would also give you 9/8. So both of those things are the same. If we could do or. And so that defines the tone, which is a very common step when we're talking about musical scales. Okay, so if we talk about, like, let's say the most famous scale in Western music, the one that everyone learns when they first take piano lessons or whatever musical instrument you're learning to play, the first scale that you normally learn is the major scale, and often it's the C major scale. And so in general, these scales are just collections of tones, usually within an octave, and then we just consider the same collection in the next octave and the next octave. And the relation between the tones is typically some simple intervals. So with the C major scale, one way to define that is to say that you start on C and then you go up one tone, which is the interval we just defined, to D. And then you can define the next note by saying that it's a major third above the C, and the next note by saying it's a fourth above the C, and then a fifth, and then a sixth. And then the last note, B, you could say that's just a tone above the A. And so if you work all that out, then you get the following frequencies relative to the frequency of C. So 1, 9/8, and so forth. And if you play that scale, it's going to pretty much have the same character regardless of whether I start on a C on the note that I just started on, or if I start on some other note. If I have the same ratios of frequencies for my notes, then it's going to have the same character. So if I start that on, say, a G, we could recognize it as being the same pattern of pitches, just moved upward by a fifth from the original scale. Okay, so this is kind of generally how scales work. You just choose some particular collection of notes within an octave. It could be 5 notes or 7 notes or even 12 notes. And you specify what notes they are by saying what are the frequency ratios between the various notes, or what are the musical intervals between the various notes. Okay, so that particular way of defining the major scale in C is what's known as just intonation. It uses fifths and fourths and thirds in order to define the scale. I'm going to actually mention 2 other ways of defining almost the same scale with slightly different frequencies. And so those are different intonations of the major scale in C. And so to introduce the next way that we can think about this C major scale and a lot of other scales, I want to talk about a very simple thing you can do starting from the interval of a fifth. Okay, so there's something called the circle of fifths or the cycle of fifths, which is a procedure where you start with some note. I'm going to assume that's a C, and then you just go up a fifth, and then you keep going up a fifth each time. And so, for example, if I start from C, then I would get up to a note we call G, and then D, and then A, and then E. And what we can do then is to take those down so that they're all in the same octave. So I'll just play how that sounds. So we would go. So that spans more than 2 octaves. But if I then take the D down an octave and the A down an octave and the E down 2 octaves, so then they're all in the same octave, then we get the following scale. Or if I keep going, and so that's a 5-note scale that's called the major pentatonic scale. And this is one of the most prevalent scales in all of music, not just Western music, in various Chinese pieces and Indian music. This particular pentatonic scale comes up all of the time. And you can see that sort of mathematically, it's a very natural thing because it just comes from taking notes that are separated by a fifth. If you just take the same set of notes but start on a different note, so you could play the scale starting on an A, and that's another very common scale, which is the minor pentatonic scale. So if we continue this procedure, so instead of stopping at E, we could go up another fifth and go up another fifth. If you add 2 more notes to your scale that way, then it turns out that the set of notes you end up with is exactly this set of notes that we had in the major scale. Okay, so if you want to get C major, you start on F, and then you go up a fifth and 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 a fifth. And the final collection of notes that you have is then the same set of notes that we had for the C major scale. If once you bring them down to the same octave, then the relationship between the notes looks like this, where you go up a fifth and down a fourth and up a fifth and down a fourth. So this is, as I mentioned, it's the first scale that most people learn when they're taking music lessons. It's the most prevalent scale in Western music in the past few hundred years, and actually even all the way back to the ancient Greeks, they called this the C Ionian scale. And if you start that scale on various different notes, Then there are other names for the scale. So the Ionian scale is the familiar major scale. But if you start on the D instead of the C, you get the Dorian scale. Or the G is the Mixolydian scale. So there are names for each of these different ways of playing it. People call those modes of this major scale. Okay. And so of course these are the notes that are the white notes on the piano. But we could even add more notes. Of course, that's not all of the possible notes. And if you continue going up by a fifth, then there are additional notes that come in. So if you just add one more note, you get an interesting 8-note scale. So that's with an F sharp. So let's just play that one. That's interesting because it comes up a lot in jazz music. It would be called the bebop scale in the key of G. So it sounds like this. It's a little weird to be hearing that with a choir. And you can just keep going and adding more notes, and eventually you almost come back to the same note. After you go 12 fifths up, then that's almost exactly 7 octaves. Okay, and so once you do that, then you get this set of 12 notes, which is what we call the chromatic scale. So it's natural in the sense that all we have to do is think about the interval of a fifth and the interval of an octave to bring things back down to fit within a single octave, and then you just get all the notes of the chromatic scale. Okay, so I want to talk a little bit about, get back a little bit to the fact that we had multiple ways of defining the C major scale. So I want to talk about what would be called like different intonations for this scale, or different tunings for this scale. And so I'll just remind you that the first way that I defined the major scale, that used the interval of a fifth and an octave to define the fourth, and also used the interval of a major third to go from the C to the E. We said that was a major third. So that's a little bit different, it turns out, than the notes of the Pythagorean, than the notes of what's called the Pythagorean version, where we just use fifths. So we go up a fifth and then up another fifth and down an octave, which is the same as going down a fourth, and then up a fifth and down a fourth, and so forth. Okay, so you could have these relationships between the notes, or you could have these relationships between the notes. And the frequencies of the E, the A, and the B are actually just slightly different. So this one is called Pythagorean tuning. This one is called just tuning. And you might be wondering, well, which is the one that we normally use? And actually, it turns out it's neither of these. So what we normally use is something called equal temperament. And I want to explain that to you now. Okay. So in order to explain that, let me go back to this chromatic scale, where we defined it by starting from C and then going up or down musical fifths until we got a collection of 12 notes. And so if you rearrange all of those, you get a set of notes that fit in an octave, and they're almost equally spaced. But actually, it turns out they're not quite equally spaced. If I define the chromatic scale in this way, using fifths, then and using this exact 3:2 ratio for the fifths, then there's slight differences in the spacing. So the distance from C to C sharp is not the same as the distance from C sharp to D. And so if I were to play a specific combination of notes like C, E, G, and then I just move all three of those up, and I go to C sharp, F, and G sharp, then it wouldn't sound the same in this version of the chromatic scale. So the solution to that, I mean, that maybe it's not a problem, but what we're used to is on a piano when you play a certain chord and then you just move it up each one semitone, then normally we're used to that sounding the same or having the same qualities. So we can basically fix this by changing the ratio that we define to be a fifth to a slightly different ratio. So we can adjust this, and if we took this ratio 1.4983 instead of 1.5, and then we define the chromatic scale again using this series of fifths, then we would get exactly back to the same note after 12 steps. So 12 of these steps would be exactly 7 octaves, whereas 12 of the 3/2 steps is not quite 7 octaves. Okay. And so a different way to say this is that we could, instead of defining everything using fifths, we could just start from the assumption that we want all of our chromatic scale notes to be equally spaced. And so that means that we just want to divide our octave into 12 equal parts. So as we said in a previous lecture, the frequency ratio that achieves that is just 2 to the power 1/12, which is 1.05946, and it keeps going. And so in our usual way of defining the chromatic scale, or the modern way of defining the chromatic scale, which is known as the equal tempered scale, we just define this as the musical interval corresponding to one semitone, and we define all of the other musical intervals in terms of some number of these semitones. So, for example, a fifth is 7 of those semitones, and that works out to 1.4983. A major third is 4 of those semitones. So it's an interesting exercise to work out what is the difference between the major third as we defined it before. So that was a 5-to-4 ratio of frequencies, and the major third as it's defined in this equal tempered scale. So I want to give you that problem to just think about briefly. So maybe work out the frequencies corresponding to a major third above an A with 440 hertz. Work out the frequency in the just tuning, and work out the frequency in the equal tempered scale, or sometimes it's called well tempered, and see how they compare. Okay, so let's try that. So we'll start with the just tuning. That's the easiest calculation here. And so in that case, what we want to do is take 440 hertz and then multiply by the ratio of 5/4. And so that just gives us 550 hertz. Okay. Now with the equal temperament, we want to do something a little bit different. So we want to take 440 hertz again as our starting point. But now we want to multiply by 4 of these semitones. So 1.05946. And then we could just take the 4th power of that, because we have to multiply by it by like 4 times. And let me just get my calculator out here. So that works out to 1.05946. 4th power, and then 440. Okay, so that works out to 554.36. Okay, so it's not super close. Actually, the fifth is a lot closer. The third is here, we notice, is off by 4.36 hertz. And it's something that we can hear. So I'm going to demonstrate that in a little bit, how the two sounds differ in the context of a chord. But first I'm going to introduce the idea of chords in general. Okay, so before we finish this discussion, I want to just quickly flash the picture of all the different frequencies that we would get for the notes of the equal tempered chromatic scale. Okay, so those are defined by exactly equally spaced intervals. And then this is the one on the left. This would be if you start with C and then go up a fifth with the 3/2 ratio, and then up another fifth and up another fifth, and then bring everything down so it fits in the same octave. So you go up to an F sharp and then down to an F sharp. And so then you can see that there is a little bit of a difference between the various intervals that show up. And actually, one interesting thing is that top F sharp is actually slightly higher in frequency, about a quarter semitone higher in frequency than the bottom F sharp. So 12 fifths is slightly more than 7 octaves. And there's even a name for that little interval, which is the difference between 12 fifths and 7 octaves, and it's called the Pythagorean comma. So that's a good one for your trivia night. Okay, so getting to our discussion of chords, we talked about scales, which are various collections of notes that maybe we play at different times in a melody, and those have simple relationships based on musical intervals. So chords are basically just when we play several notes, but we play them at the same time. And again, the chords that we normally use involve notes that are separated by these very simple intervals. Okay, so the major chord is maybe the most famous, where you have a major third and then a minor third, so like C and then E and then G, and you play all of those at the same time. So that's a 5-to-4 ratio for the major third, and then a 6-to-5 ratio for the minor third. And so the frequencies of these three notes are 4 to 5 to 6. If you want to play those notes but in a different order, then you can get an even simpler relationship. So in playing that chord in what's called the second inversion, so G, then C, then E, you have a 3 to 4 to 5 ratio of the note frequencies. Similarly, a minor chord is just switching those two intervals, so a minor third and then a major third, and that has quite a different quality to it. If you work out the frequency ratios, that one is a little bit more complicated. It turns out to be 10 to 12 to 15. So one of the cool things about a major chord is that if you think about the three notes in the chord, and then also all of their harmonics, all of those pure tones fit into one harmonic series for a note that is an octave, or sorry, 2 octaves lower than the bottom note of our chord. Okay, so if I play this chord, so you have all of these tones indicated. The red ones are the pure tones associated with the C. The green ones are the pure tones associated with the G, and the black ones are the pure tones associated with the E. And these blue lines represent all of the different harmonic frequencies of this note. So it's fascinating that when I play this one note, oops, not that one, this one. Okay, even though our brain hears it as one note, it actually has all of the frequencies already present that are in this entire chord. So that's probably part of the reason why we hear that as being so harmonious. It's very, very natural for us to hear those things together, because we hear them together every time we hear a musical note, which is not just a pure tone. And so just getting back to this question of the various tunings of the notes. So I wanted to end with a bit of a demo. And so we have the just tuning definition, where the frequency ratios are just 4 to 5 to 6 precisely. And then what I was saying is that when you change up the definition of a major third to be 4 semitones and a minor third to be 3 semitones, you get these slightly different frequencies for that chord. If I went with a Pythagorean tuning, where the major third is up a fifth and down a fourth and then up a fifth and down another fourth, then you get even this third frequency for the E in the chord. The top frequencies are pretty similar. So we're going to demonstrate what these 3 different cases sound like. Okay, so let me just load up my tone generator. Okay, so let's go with, we'll start with the Pythagorean tuning. So 556.9. So this one's actually furthest off from the simple interval. So let's hear what that sounds like. Okay, and so now I'm going to switch the middle note to the equal temperament, and then I'll switch it to the just. Okay, here's just. And then back to Pythagorean. And back to equal. Okay, so what I hear when I listen to the case with the Pythagorean or the equal temperament is that you could actually hear a little bit, something that's a little bit like the beat phenomenon that we saw last time. And in fact, it really is, I think, related to that, because when you have the 556.9 or the 554.4, what happens is that, see, you notice how the harmonics of this E line up perfectly with the harmonics of the C. Well, that would be for the just tuning. But if I change up the E a little bit, then these harmonics are no longer going to line up perfectly. There'll be a difference of a small number of hertz. And what we're going to perceive then is that the beats coming from the 2 harmonics, which are almost but not exactly equal in frequency. Okay, so that is it for today. And the next video, we're going to talk about some interesting hearing versions of optical illusions.